In 1999, Quake III Arena revolutionized 3D gaming. To compute reflections, lighting, and physics in real time, the game had to normalize millions of vectors every second. But doing this with standard math was impossibly slow for 90s hardware. Normalizing a vector requires dividing its coordinates by its length. Mathematically, this means multiplying by 1 over the square root of x. This specific term, 1 over the square root of x, is the computational backbone of 3D computer graphics. In the late 90s, division and square root operations were hardware nightmares. While an addition took a single CPU cycle, a single floating point division could drag on for dozens of cycles, grinding the entire game engine to a halt. To break this bottleneck, developers exploited how computers store decimals in memory. Under the IEEE 754 standard, a 32-bit float is split into 3 parts, a single sign bit, an 8-bit exponent, and a 23-bit mantissa. Here is the genius realization: if you treat the binary representation of a float as a plain integer, it behaves almost exactly like a logarithm curve. By subtracting a correction factor, mu, we get a highly accurate linear approximation of log 2, x, directly from memory. Taking the logarithm of both sides of y equals 1/sqrt, x, reveals a simple linear relationship. By bit-shifting the float's integer representation right by 1 and subtracting it from the magic constant 0x5f3759df, we compute a jaw-droppingly close estimate of 1/sqrt, x, instantly. But the bit shift guess is slightly dirty. To polish it, the algorithm runs a single iteration of the Newton-Raphson approximation. Using tangent line convergence, it quickly snaps the raw bit-shifted estimate right onto the true inverse square root curve. This incredible hack was 400% faster than standard division. It saved Quake III's frame rates and remains one of the most elegant, mind-bending examples of squeezing pure mathematical beauty out of physical hardware limits.